So lesson 6 is on limits and continuity. Okay, we've been all over limits, but this is your first introduction into the true definition of what makes a function continuous. Okay, so now that we have an understanding of limits and are using limit notation, we're going to use limits to define continuity at a point. And this is in bold and italicized. This will be very important throughout our course. I guarantee you're going to write, see that definition of continuity box? You're going to use that on the AP exam. Guarantee it. Okay. Defining continuity at a point. All right. Use the graph below to complete the table. You should look for 3 conditions that are necessary to satisfy the definition of continuity. That is, what 3 conditions must exist in order for f of x to be continuous at point C? Okay, so here is your definition of continuity. It has 3 parts. You have to always have all 3 parts. And you cannot skimp corners. So for something to be defined, and I'm going to say at x equals c, okay? For something to be defined as continuous at a particular point, then f of that value is defined. So no asymptotes, no holes that aren't filled in somewhere else. It has to be defined. It has to exist. The function, has to exist at that x value. Okay. The other thing that has to happen is that the limit as x approaches c of f of x exists. Okay, now you know that for the limit to exist, the limit as x approaches c from the right of f of x must equal the limit as x approaches c from the left of f of x. So that shows you how a limit exists. The limit must exist for you to be continuous. So the limit has to exist and the function has to be defined there. But these 2 things alone does not guarantee continuity. F of c can be defined. Look at this. This is c. F of c is defined? Yep, there he is. Limit exists? Absolutely. From the right and from the left, he exists. But guys, is that function continuous? Absolutely not. It has a pothole in it. So not only do these first things have to be defined and have to exist, they have to equal each other. The limit as x approaches c of f of x must equal f of c. They have to be in the same place. That's what picks that dot up and plugs that hole. If they're equal, now we're continuous. So you have to say all 3 parts. Number 1, the function is defined there. Number 2, the limit exists there. And number 3, that the limit equals f of. Okay, so here's what we're going to look at. And we're not going to do all these. So find the function value if it exists for the given x value. So this we're finding f of c. Super easy. Find the left-hand limit, find the right-hand limit. Okay, so we're going to look at it from both sides. These 2 are going to tell me if the general limit exists. Okay, so once we prove this guy and show that they're equal, then I know this guy. Then I have to compare this box to this box. If those 2 are the same, then we are continuous. Okay, so let's look at 9. So 9 is here. That looks like a hard stop. So here we go. F of 9. I'm going with 3.5. Left-hand limit, 3.5. Right-hand limit. Well, he doesn't exist on the right-hand side. I can't fly in from the right-hand side. Does not exist. Okay, since the left-hand limit does not equal the right-hand limit, then the overall limit does not exist. And then this 3.5 and the overall limit don't equal each other, so is it continuous? No. Okay, let's look at, no. Let's look at 0. All right, at 0, and I'm looking at this function, and it looks like super well behaved at 0. Straight, filled in, no holes, doesn't even have a turn. Like, it looks good. So I'm going to predict that we're continuous at 0. It feels like this makes you question everything you just sort of already assume. So x equals 0, f of. So I'm looking for f of 0. F of 0 looks to be 6. Left-hand limit, 6. Right-hand limit, 6. Overall limit, I agree. Does f of equal the overall limit? Yes. There you go. Okay, what's the one down here? -3. Okay, now watch what I'm going to do because I don't want to scroll. I'm going to take this dude out, and let's make him -3. Okay, so -3. Ooh, yeah, this is a good one. So there's -3. So I need to know what is f of -3, and that's this dude down here. So that's -6. Left-hand limit, 1, 2, 3, 4, 5. Right-hand limit, 5. Remember, the limit has nothing to do with where it is, it has to do with where it's headed. Well, if the left-hand limit and the right-hand limit are the same, then the overall limit exists. So the limit exists, and the function is defined. However, those two things are not equal. So are we continuous? No. And you guys can see it. It's not continuous right here. There's a big old hole. Let's look at x equals -5. Okay, so again, I'm going to mark this guy out just so I don't have to scroll. So x equals -5. Okay, that's here. So f of -5, that's the filled in hole. That's that guy. So he's a -2. Limit from the left looks to be -2. Limit from the right, that looks to be 7. Left and right limit do not equal each other, so the overall limit does not exist. There's the f of, there's the overall limit. So no, it's not continuous. So I know that you guys can look at this and say, oh my gosh, look, I mean, there's this huge break right there. There's a huge jump discontinuity. So no, it's not continuous, but you have to be able to write it. And that's what we're going to practice. While limits told us where a function intended to go, continuity guarantees that the function actually made it there. Oh, that's a powerful sentence. Let's do that again. While limits told us where a function intended to go, remember we said it didn't have to actually get there, it was just where it was headed. Continuity guarantees us that the function actually made it there. All right, classifying types of discontinuities. So I have removable and non-removable. Removable is a point. It's a hole. It has a two-sided limit that exists. It just has a hole in the middle of the road. That is a removable or a point discontinuity. It is super self-explanatory. This has a removable discontinuity at x equals 1. This has a removable discontinuity at x equals 1. The limit exists from both sides, both headed to the same place. However, when you get there, there's nothing there. It's a hole. Jump discontinuity means that the one-sided limits exist, they're just not equal. One more time. the one-sided limits from the right and from the left both exist, however, they're not equal to each other. That is a non-removable jump discontinuity. Non-removable, because it's not a point, jump discontinuity. Okay? And then you have an asymptote. So asymptotes are where you're headed to positive infinity and negative infinity, and that's when they're saying the one-side limit doesn't exist because they're saying infinity is not a place. So if your limits are headed to infinity, then it is an infinite discontinuity, a non-removable, because it's not a point, discontinuity. An infinite discontinuity. And look, the top one has an asymptote on both, but the bottom one, the left-handed limit is headed to a number. It's headed to 2, but the right-handed limit is headed to negative infinity. So it just has to be one of them that is headed to infinity. Okay? Find the points, intervals, at which the function is continuous, and the points at which the function is discontinuous on the interval from -5 to 10. So it's asking me two questions. I want to know, where am I continuous and where am I discontinuous? All right, I am continuous, and I'm supposed to start at -5. I am continuous from here to there. So from -5 to -3, parentheses. And union, I am continuous, oh, hold on, all the way. I don't have to stop here because he's filled in. So all the way to there. So what is that? 3? So from -3 to 3. And so we got some sort of asymptote action going on here at 3. So he's gonna be good to here. So that's 5. So from 3 to 5, continuous. And then from 5 to 7, continuous. And then the last one from 7 to 10. Notice all those got parentheses. Now I am discontinuity at specific places, not intervals, places. So I am discontinuous at, first place is -3. I am discontinuous, and I'm going to label what kind it is off to the side. I am discontinuous at +3. I am discontinuous at 5. And I am discontinuous at 7. Now, at -3, I am removable, point discontinuity, or a hole, aka a hole. At 3, that looks like a vertical asymptote to me, so that is a non-removable infinite discontinuity. At 5, I am non-removable jump discontinuity. No, nope, I'm not. That is a lie. I was looking at the next one. 5 is a hole. 5 is, sorry, removable. My bad. He is removable, point discontinuity. 7 is the non-removable jump. Sorry. Non-removable jump. Okay. Definition of continuity. More facts and theorems. Yay! One-sided continuity is really not a big focus. I'm going to slide right over that. Here we go. Let's look at continuity at a point. Suppose f of x is defined on an open interval containing x equals c. Then f is continuous at c if the limit equals where it's defined. Again, this ensures that where it's headed, it actually gets there, that those are the same place. Continuity on an open interval. A function is continuous on an open interval, a, b, if it's continuous at each point in the interval. Continuity on a closed interval. A function is continuous on a closed interval, a to b, if it's continuous on the open interval, a to b, and the function is continuous from the right and the left, from the right of a and the left of b. So what this is saying is this is continuous on an open interval. So like if I had a function that stopped here, did some stuff, and stopped here, then this is, and let's call him A and him B. He is continuous on A to B. He is not continuous on A to B. Because for him to be continuous on a closed interval, the function has to be continuous from the right and from the left from A and B. So it has to still exist beyond for you to get the brackets. Not a huge concept, okay? So don't lose sleep over that one. Continuity laws of some basic functions. Polynomial functions are continuous forever. X squared, x cubed, x to the fourth. All of your just well-behaved, no asymptotes, no holes, nothing weird going on, nothing is undefined, just your good polynomial function. They are always continuous. Your rational functions are always continuous except where you have a vertical asymptote, which is where the bottom equals 0. Y equals x to the 1 over n really doesn't pop up that much. Continuous on all reals if n is odd, and continuous on all positives if n is even. Again, don't lose, I mean, that's a fact. It's very true, but don't lose sleep over that one. Sine and cosine graphs. Okay, so don't think of the unit circle. Think of the sine graph and the cosine graph. And you know they go on in both directions forever and ever and always. They are both very continuous. They're very tame functions. They're very well behaved. Y equals b to the x is continuous. That's your exponential function. And remember, they look like this. They are continuous for all x's, forever to negative infinity and always to positive infinity. It says if b is greater than 0, but I think I would disagree with that because well, that would make it negative, so then it would flip. No, yeah, I would disagree with this. Because if b is less than 0, b is negative, that just causes a flip, but it's still continuous from positive infinity to negative infinity. Logs, okay, now logs are tricky. Logs start here and their asymptote is behind them. So that's why you see the x's have to be greater than or equal to 0. Inverse functions. Okay, inverse functions are continuous. Now remember, when you do inverse functions, the domain and range flip-flop. So it's continuous on an interval with the range, and if f inverse exists, then f inverse is continuous on the domain R. Don't lose sleep over this one. No big deal. Just breezing right past it. No worries. All right, properties of continuity. Yep, don't need any of those. We're good. Moving on. Okay, this is a big one. For c equals -3, c equals 3, and c equals 7, find f of c, the left-hand limit, the right-hand limit, the overall limit, and tell me if you are continuous. Okay, now this one's going to be the pain in the butt because we're going to pretend this is an FRQ and we're going to write not what we think we need to write, but what they think we need to write. Okay, so first I'm going to do C equals -3. So the first thing I need to find is f of -3. So f of -3 looks to be 2. Okay, the next thing I'm going to find is the left-hand limit. So -3 from the left of f of x, and then I'm going to find the limit as x approaches -3 from the right. Just going to go ahead and write both of those. Okay, -3 from the left, -1. -3 from the right, -1. Okay, now because of everything we established in number 2, I can now conclude that the overall limit as x approaches -3 of f of x equals -1. Okay, however, this sucker and this sucker are not the same. So, at x equals -3, f of x is not continuous. But you have to state why. Because f of -3 does not equal the limit as x approaches -3 of f of x. It's hard to talk and write that at the same time. Okay, so this is your conclusion. Okay, let's look at 3. Can I just talk through these? Let's talk through these. You've seen one written. So you know you have to find him, you have to state what he is. To get to this guy, you have to do both of these. Then once you establish this, you compare them to him. If they're the same, you're good. If they're not, you're bad. You just have to state all that. Okay, so let's just talk through. Don't write, just talk. Okay, so for C equals 3, here's 3. It's an asymptote. I can see that. Okay, so if I'm looking for f of 3, he does not exist. It's an asymptote. So f of 3 does not exist. All right, the limit. The limit as x approaches 3 from the left is headed to positive infinity. The limit as x approaches 3 from the right is also headed to positive infinity. Therefore, the limit as x approaches 3 of the function is infinity. F of 3 does not exist. So at x equals 3, f of x is not continuous because f of 3 does not equal the limit as x approaches 3 of f of x. Okay, let's look at 7. Okay. F of 7 equals 3. It's a lot of 3's in this problem. Okay, so there's the first dude. Now the limit from the left, 3. Limit from the right, 6. Overall limit does not exist. F of 7 is 3. Overall limit does not exist. Therefore, not continuous because f of 7 does not equal the limit as x approaches 7. All right. It's easy to think through. They're difficult to write. And that's what you've got to be good at. You got to practice writing, which we will. Okay, confirming continuity over an interval. You must be able to perform continuity without a graph or a calculator by using your knowledge of the behavior of the parent functions and their transformations. Determine whether each function is continuous or not. If not continuous, justify your answer by using the definition of continuity. So no calculators. All right, I look at him, I know he's got issues at 3. Notice it's not asking me if it's continuous at a particular point. I want to know if the function is continuous or not. So I have to think about his whole life. And this sucker is fine for his whole life except at 3. So I'm going to state that f of 3 is undefined. Now, I know that that causes an asymptote because it's in the denominator of a rational function. So I am going to find the limit, because I have to prove it. I already know he's not continuous, but I have to prove it. I'd find the limit as x approaches 3 from the right of 1 over x minus 3. Okay, so I know that because this is an asymptote, I'm either headed to positive infinity or negative infinity. I should figure out which one. Well, if I'm headed to 3 from the right, what I'm going to do is plug in a number that's slightly bigger than a 3, so like a 3.1, which we've already done this in a previous notes. So this would be 1 over a 0.1. Everything's positive. I'm doing 1 divided by a tenth. It's going to get large, and it's going to be positive. So I know that the limit from the right is headed to positive infinity. Okay, now I'm going to find the limit as x approaches 3 from the left. So now I'm going to pick a number that's just to the left of 3. So I'm going to go 2.9. So now that's a negative tenth. Well, 1 divided by a tenth is going to be very big, but this is a positive divided by a negative, so I know he's headed to negative infinity. Okay, well, I've just proved that the right and left-hand limits are not headed to the same place. So I can say that the overall limit of f of x does not exist because the limit from the right of f of x does not equal the limit from the left. Okay, and yes, it's a pain in the rear end, but you have to write all that stuff. Okay, so all of this was just for the limit. Now I haven't addressed the continuity yet. Okay, so I can say f of x is not continuous at x equals 3 because f of 3 does not equal the limit as x approaches 3. And I have all my work to prove that. So I know what's going on because of my pre-cal knowledge. I know that he has issues at 3. I know it's going to be an asymptote. So I know we're talking about infinity or negative infinity. And sometimes they head to the same place. Sometimes it's all good and sometimes it's not. But I also know that right off the bat, this sucker's undefined. So I know he's not continuous. So I know the answer right off the bat is not continuous. But I have to have all the documentation there to prove it. Okay, this guy has issues at -2 because that's on the denominator. So now I need to use my pre-cal knowledge to figure out if that's an asymptote or a whole because those are two very different issues. So let's see. I'm going to factor the top. 6, 3, and 2. 2 and 3. There it is. Because that's 4 and 3. That'll give me a 7. All right, they cancel. So I know it's a whole. I know there's a whole at x equals -2. So that's where I'm going to focus. I'm going to find f of -2. Well, if you plug in a -2, now I remember in the previous notes, I would say, okay, so now take the -2 and plug it into what's left, and that will tell you where the whole is. Okay, but please know that I'm doing something different here. I'm asking, where is the function at -2? Well, he doesn't exist. There's a hole there. Plugging the -2 into here and getting -4 plus 3, a -1, tells me that I have a hole at -2, -1. It does not say that f of -2 equals -1. Make sure you know the difference. Okay, so I already know he's not going to be continuous. I have to prove it. From the right. -2 from the right. So I'm going to take, well, I can just plug in a -2. All right, so here's why. If I'm headed to -2 from the right, if it's an asymptote, that's when you need to creep in from either side. But guys, this is just a flat out hole. So I know that these two limits are going to equal each other. Like I know the overall limit's going to be fine. So to find where the hole is at -2, this is when you take what's left and plug in a -2. That limit is going to be a -1. The function doesn't exist there. The hole is there. The function doesn't exist because the hole is there. But because it's a hole and not an asymptote, the limit is headed to a particular spot. So the limit as x approaches -2 from the left is also going to be -1 because I'm taking the -2 and I'm plugging it in there. So I know that the overall limit exists. However, and I'm not going to write this, we are not continuous because f of -2 does not equal the limit as x approaches -2. All right, good times. Removable discontinuity, piecewise function. Use the definition of continuity to find the value of k so that the function is continuous for all real numbers. Okay, I want this piecewise dude to be continuous. What that means is the two pieces of the piecewise function have to meet. They have to connect. If they miss each other, then I'm not continuous. So if they meet, think about what that means. So sometimes piecewise functions do, like you can have this and it stops, and then you have something doing this, and there's an open circle there, and they don't meet. But sometimes they meet. But it's still two pieces of a function taped together. So what I need is I need for this guy to equal this guy at that spot. Just that spot. So here's what I need. I need kx squared to equal kx minus 6 at the break, x equals 2. Okay, let's go back and read the directions. Using the definition of continuity, find the value of k. So I want k. And I need to know what k is when x is 2. So if I plug a 2 in here, okay, let me write this so it looks normal. It's just an equation. I'm going to subtract my 2k, and I'm going to get k equals -3. But you have to use the definition of continuity. I haven't done that yet. Use the definition of continuity. Okay? Continuity says f of 2 has to equal the limit as x approaches 2. That is the definition of continuity. Okay, so f of 2 is, if I take a 2, hold on one second, and plug it in here. So if I think k is a -3, let me change colors. All right. Let's rebuild our piecewise function now that we think we know what k is. So if k is a -3, this would be a -3x squared. And if k is a -3, this would be a -3x minus 6. X is less than or equal to 2, x is greater than 2. Okay. So I need, and I've got f's, and I should have g's, but you know. So I need to find g of 2. Well, g of 2 going into a piecewise function will go into this top one. So if I plug a 2 in here, 2 squared is 4, and 4 times -3 is a -12. So g of 2 equals -12. Okay, now I need to find the limit. So I need to change colors again. The limit as x approaches 2 of g of x from the right. Okay, from the right. Okay, go back to your piecewise. From the right, I would be this one. So I'm going to plug in a 2 into this one. And if I plug a 2 in there, that's -6 minus 6, that's a -12. Ooh, that's good. All right, now let me find a limit as x approaches 2 from the left. And if I do that, this one, because these are the x's that are from the left. So let me plug in a 2 here. 2 squared is 4. 4 times -3 is -12. All right, looky, looky. I'm out of room, but this is what I would write if I had more room. First, I have to define that the overall limit exists. So I would write the limit as x approaches 2 of g of x is -12. And that's the conclusion from these two puppies. Okay, so that's the overall limit. Then I can state that because I have g of 2 right there, and I know the overall limit, and I've just proved that they're both 12. Whew. Okay. Let's skip h. I think we're good with skipping h. Oh yes. Let's go look at number 5. He's a big one. Let's do this one. Okay, we've got 3 pieces. I've got a piece on the left, a dot in the middle, and a piece on the right. I'm linear on the left, a dot in the middle, and quadratic on the right. For what values of x is h not continuous? Okay, well, all the action happens at -2. I know this is a linear function. He's continuous. That's just a dot. And I know that's quadratic. He's continuous. So I really just need to figure out what happens at -2. So first I'm going to find f of -2. Well, which function do you plug that into? I have 3 different pieces. Well, the only function that's defined when x is a -2 is this one. So he's 3. Okay, now I need to fly in from the left. Nope, I'm not headed to a 3. My bad. I'm headed to a -2 from the left. Okay, so which piece would I go into? From the left. That would be this one, because these are the values to the left. So if I'm flying in on this one towards a -2, so -2 times -2 minus 5. So that's a +4. Minus 5 is a -1. So I can already tell I'm not going to be continuous because these two numbers don't match. The limit as x approaches -2 from the right. Okay, from the right, that's this guy. So let's plug a -2 in here. So -8 plus 12 plus 3. So 4 plus 3, that's a 7. Oh, heck yeah. None of these things meet. The two functions don't connect. The dot doesn't connect. They are all over the place. Okay, so what I have to state, and I didn't write it out in the last one, and I know we skipped the problem before this, so let me write this one all out. So because of this, I know that the limit as x approaches -2 of f of x does not exist. Right and left hands are not the same. I also know that f of x is not continuous at x equals -2 because, now think about your definition, f of -2 does not equal the limit as x approaches -2 of f of x. That's the definition of continuity. Okay. Now, before school started, I gave you a couple videos that I wanted you to watch, and one of them was on systems. So, we're going to put that knowledge to the test. Use the 3-part definition of continuity to create a system of equations. Then find the values of a and b so that f is continuous for all real numbers. Okay. If I'm continuous, then all three of these pieces have to connect. And obviously they're going to connect at 6 because that's that middle dot. So I'm at -1 and I'm hoping it all converges at a 6. So here I go. I need this guy. I need to know he needs to equal 6. Okay, because that would make this guy run into that guy. So I need those two to be equal, but not everywhere. I need them to be equal where they're cut. So at x equals -1. Okay. I also need this guy to equal this guy. So I need ax squared plus b to equal 6 at x equals -1. Okay. Well, the goal said find a and b. Well, I know what x is, so I'm going to plug some x's in. So -1. So I'm plugging a -1 in here. So that's going to make that -2a minus b equals 6. And then I'm going to take that x equals -1. I'm going to plug him in there. I'm going to square them. It's going to be +1. So that's going to be a plus b equals 6. Okay, I am now going to take these two suckers and I'm going to put them together and make a system. Now, this one's really nice because the b's cancel. So this is elimination and the b's are going to cancel. If nothing canceled, then you would have to put parentheses around something and multiply and make something cancel. But this one's nice. They already cancel. You're going to add down. So -2a plus 1a is a -a, and 6 plus 6 is 12. So a equals a -12. Okay, well now I know what a is. I'm going to go right there. -12 plus b equals 6. Add the 12. b is 18. And there are a and b, so that it's continuous. Okay, now hold on, because I would not get credit for this problem, because the directions say use a 3-part definition of continuity. I have not done that. So here's my 3-part definition. The 3-part is, first of all, find f of -1. Well, f of -1 is a 6. All right, and then I have to find the limit. The limit as x approaches -1 of f of x. Okay, so I have to find from the left and find from the right. The limit as x approaches -1 from the left. That's going to be this guy. And when we plugged in, we got to plug in our a and our b. This problem is so much fun. Okay, so if I plug in, because I have to go into this. So 2 times a, and a is -12. So -24x minus b, minus 18. There you go. That's the dude I need to take the limit of as x approaches -1. So if I plug a -1 in here, that's a +24 minus 18, that's a 6. Okay, now I got to do the limit as x approaches -1 from the right. Okay, so that would be this guy. So now let me go build him up with the a's and the b's. So if a is -12, so -12x squared plus 18, and I'm headed to -1, that would make that a +1. That's still a -12. That would make this a 6. Okay, so now I can say that limit is a 6. Aren't these a pain in the rear end? All of this helps me find that. Now I can state the definition of continuity, that f of -1 equals the limit as x approaches -1. Therefore, we are continuous. Okay, that's the last big mamma jamma. These are shorter. You know the function value and the limit value can exist independently of each other. Let's summarize the big ideas of continuity on intervals at points and one-sided limits. So I have a piecewise function, the split is at 3. Find each of the following. So I want the limit as x approaches 3 from the left. You know what? I bet y'all could find all this. Why don't you pause the video, finish these up, then hit play, and check your work against mine. All right, so the limit is x approaches 3 from the left. That would be this guy. So 7. The limit as x approaches 3 from the right. That would be this guy. 3, that's a 9. G of 3. That would have to be this guy because he is the equal to, so that's a 9. The overall limit of this sucker does not exist because limit x approaches 3 from the left, G does not equal the limit as x approaches 3 from the right. Is it continuous? Oh, there's those words, justify. No, it is not, because f of, no, not f, g of 3 does not equal the limit as x approaches 3 of g of x. Good times. Okay, summary. If a function is continuous at a point, then the function value, excuse me, and the limit value are the same at that point. That's all this says. The function value and the limit value have to be the same.